This is just testing some random components to see how this tester fares against DMMs. Okay, let's start with the T7 measuring a simple diode. Just stick it between pin 1 and 3. No, 1 and 2. Okay, so we have diode between pins 1 and 2. And it says that the forward voltage is 648 millivolts, 36 picofarad capacitance, and the reverse current 87 nanoamps. And it gives a picture, of course, of which is the anode, which is the cathode. So that's quite a bit of information. A meter like this doesn't even have a diode scale. This meter does. So if we connect it up to this meter, put it to the diode scale, and it's reverse bias, so we get overload. Okay, so here it is. On this meter, it's measuring the forward voltage at 0.514 volts, and that's all the information we get. So let's try an LED. And you can see it flashes it. So it's a white LED because we can see the color. We can see the anode cathode, and we can see that it's 2.91 volts and 15 picofarad capacitance. This guy is still saying it's over voltage, so it cannot measure this LED because the forward voltage is too high for this meter. So of course I have another meter here, which is a big Keysight, and it has a diode scale, and it can measure it, and you can see that it's lighting it up at white. It says it's 2.64 volts forward voltage. So depending on the meter, you may or may not be able to measure an LED, and you may or may not be able to tell the color. But with the T7, it gives you the color, and it tells you which is the anode, cathode, and it can certainly measure the voltage. In fact, this thing can measure Zener voltages all the way up to 47 volts. So in that sense, this is much more flexible than your average DMM. Now let's try this meter with a little transistor. This is a bipolar transistor, but you don't need to know that with this meter. You just plug it in and it tells you what it is. So it tells you it's a PNP transistor with a HFE of 241. It's got a VBE, voltage across the base, of 713 millivolts, and it's telling you the collector current that it's using is 6.2 milliamps. And it goes emitter, base, collector, so on pin 1, 2, 3. So it tells you which pins are which. These meters don't. So these meters don't tell you which is the emitter of the transistor. They expect you to know. So this is a PNP, and emitter, base, collector. Here you go. And we can measure the HFE down here. So this says the gain is 184. And that's all the information you get. You have to know which is the emitter and base. This one is similar. It has PNP over here. However, I found that the connector is a little flaky. It's hard to get the transistor in there. So it's saying that the HFE is 236. So these things aren't exactly saying the same thing. But they do give you some kind of idea of the gain of the transistor. This is another bipolar, the complementary pair to the other one. So this is an NPN. It says the HFE is 310, 712 millivolts across the base emitter. And again, it's EBC on pins 1, 2, 3. So EBC on the NPN side goes in this slot over here. The reason I'm using this meter first is so that I can figure out which pins are which, because it's the only one of these that can sort that out automatically. And this is saying HFE of 187. So it's a little different from this guy. And here we go again, EBC on this one. Let's see if I can get it to make contact. So again, it's reading a little higher, 257 for its gain. Here's a TIP 41, so big bipolar transistor. If I can. And NPN, the HFE is only 33, and there's only 0.546 millivolts across the base emitter. So it is going base collector emitter. Base collector emitter. NPN base collector emitter. Can sort of fit, but it doesn't. So a big transistor like this can't fit in here. We'll have to make an adapter, little cable to come out and connect to a transistor. Let's try this guy. But with this zero insertion force socket, it's really simple to connect any of these things. So this one says it's a P-channel MOSFET, and it has a threshold voltage of 2 volts, capacitance of 1.36 nanofarads, and an on resistance of 0.1 ohms. Turned off before I could read the forward voltage. 630 millivolts. I guess that's the bulk diode that's in the FET. So this guy is really giving a lot more information about transistors than these guys, and it's a lot simpler to use. So let's measure something pretty simple, like a capacitor. So it says it's 480 nanofarads with an ESR of 0.21. So 480, and now of course it's a 0.47 microfarad capacitor, as we can see by this great big color code on it. So yellow, purple, yellow. Now these guys can measure capacitance. So let's try that. So I've got it on temperature. There's capacitance. 483. So there, the other meter was 480, so that's close. Well, let's try it with this meter here, which also has capacitance. leads in the wrong slots, but won't matter for this. 477. So this one's reading a little lower than the other two, but they're all pretty close, probably within tolerance of the capacitor. Finally, let's just try a resistor. Getting some idea of the accuracy. These are 4-digit DMMs. So that's not capacitance. This is ohms. It took a while to get there, but it's 9.9, or maybe the connections are a bit flaky. 9.7 ohms. And you can see, of course, the color code tells us it's a 10 ohm resistor. And finally, it does read 10.0 ohms. This is auto ranging. And let's go to ohms on this guy. 10.1 ohms, 10.0. And on our handy dandy multitester, 10.0 ohms. So it's doing the job on all kinds of different components. Next, I'm just going to plug in a big inductor here. See what happens. It calls it a 0.02 millihenry inductor with a resistance of 0.2 ohms. Okay, let's try it with some high gain transistors. These are Darlingtons. Have to turn it on here. So the HFE, or beta, is 26.8 thousand. And the VBE is 1.21 volts. And it's using a current of 5.4 milliamps. So this is an NPN transistor. It's actually, I believe, a 2N6426, which is a Darlington. And EBC 123. NPN EBC. This is saying that the HFE is 1278, which is a little low. These transistors should have a beta that's over 20,000. And this one does say that. This guy, EBC NPN. Alright, let's see if we can make contact in here. This one's a little tricky on the connection. Not working very well. It's quite sloppy in this connector, and it's hard to make contact with all three wires, I guess. Looks like it's saying 26,000 or 32,000 when and if it gets contact, 39,000. But pretty tough to use, actually. So let's try another one. This guy is an MPS A65. I used to be into these Darlingtons a lot, I guess. So this one's a PNP, and it says the HFE is 153,000 with a VBE of 1.17 volts and 5.5 milliamps. Emitter base collector. Okay, so emitter base collector on this guy for a PNP goes in here. And let's just see if we can get that to make contact. Okay, there we go. Also reading low. It's only 1312. I'm wondering if it just doesn't have enough digits, since this thing is over 20,000. And let's see what this one says. So it's a PNP EBC. $26,000. Assuming it also doesn't really have enough digits to do this. Anyway, I guess the bottom line here is it's pretty tricky to get any kind of reasonable results from these two guys with these Darlington transistors. Whereas with this one, it's trivial. Just plug it in and you get a reading right away. You may have heard that the base emitter junction of a bipolar transistor has a fairly low breakdown voltage. So here's a way to test it out. We just stick this guy in there, put them in the Zener slot, and it says we have a Zener at 7.53 volt breakdown voltage. Cool. So if you're ever stuck for a Zener, you might just use a bipolar transistor. Although there's other considerations that you'll have to take into account, and the current curve tracer road test will actually be able to characterize those breakdown voltages much better than a device like this. Another component that may have a low breakdown voltage is something like an LED. So let's just see what that looks like. So it says we have a Zener at 21 volts breakdown. That's interesting. So if you reverse bias an LED, it does have a breakdown voltage sometimes around 21 volts.